Yeah, hi. Hello there. My voice will be limited. All right, everybody. If I I got in at 4 in the morning this morning, so I'm running on battery power at this point. So I apologize for not being able to get more to you. Uh, and I'm sure that when I was away, I actually had like one and a half of these dictations, which I call them, to do. And they were regarding this. I had done the one which was 11B, and I had started this one which is 11C. This first part, I'll go back quickly to show you what's going on. So back, and effectively, and I do not know whether I sent you that. And a lot of it's really nothing more than review, but hopefully I sent this to you. If I didn't, I will review later. And effectively, there's all these different kinds of synapses. Our focus is this axodendritic one. All of the others are modifiers, really. And so we're looking at, effectively, electrical synapses are more common in growth and development. And other than that, effectively, we're looking at really the mechanics behind how the nervous system works. And typically, depending on the neurotransmitters, and this is the neurotransmitter lecture, why it's so important, is the concept of fire or don't fire. And most nerves, unlike the neuromuscular junction, can produce more than one neurotransmitter depending on the frequency and the different impact, the different signals it's getting from the other nerves that are causing it to fire in its own way. That firing sequence may tell the next nerve not to fire or to fire. There's so much complexity. And so, without, I think it's really beyond my scope of being able to explain it to you. There's a lot of modification that goes on. And I mean, to my analogy, is always the thought process, what goes on, why you make a particular decision, why you say something you do, or do something that you do, or, when you're driving, go from this lane to this lane. All of those things are impacted by so many modifiers telling you, don't do this, wait to do this, etc., etc. And it's all about the synapse and really the neurotransmitters. And we covered this at length in the neuromuscular junction. It's really the same thing. That just happens to be a specific kind of a synapse. It doesn't have to be nerve to nerve, even though that's the crux of this chapter. That's there. And yeah, there's axons and there's a transmitter and receptors. That's effectively the dendrite. It doesn't have to be. That's the most common way that it's done. And as I said several times, it's all about the chemicals, and the chemicals are the rate determining step, and that's where we impact it. We pharmacologically impact that with any one of a variety of medicines that work on the system, work on that at that area. Okay. And so all of these are factors that are there. That's some of what that relatively brief transmission was. And we did this. So it's no different than the nerve going to the neuromuscular junction. Let's say we're looking at a signal, and effectively this signal is going to again trigger voltage gated calcium channels. Extracellular calcium is going to go in. It's going to cause effectively the synaptic vesicles to bind to an exocytose and go across the synapse, except it's not a neuromuscular junction at this particular one. Now we're looking nerve to nerve. And we have different terminology. We don't have end plate terminology. We don't have end plate potentials, no end plate. We have graded potentials, either ones that are more likely to fire or less likely to fire. That's basically it. And the same thing, if they're sufficient and they reach threshold, the ones that would be more likely to fire, what we call excitatory postsynaptic potentials versus inhibitory postsynaptic potential, we're going to get we're going to get threshold and we're going to get an action potential. It just means that the signal got far enough along to finally hit that area where there was a larger concentration or the start of a concentration of voltage, an abundance, as it were, of voltage gated sodium and then voltage gated potassium channels. That's all it means. Yeah, the synaptotagmin, that's the protein. You should remember that. Activates the snare proteins. And again, how many times do I have to say it? And more so here than in the muscle system. Remember, neuromuscular, different. We don't have that all or none phenomena. We can have calcium being reabsorbed, but not completely, so we can get that staircasing up to a certain point. We can induce tetany. You can't do that in the nervous system because of those. Remember those absolute refractory and relative refractory periods that I went over the last time. That was in that PowerPoint 11B when I sort of narrated that and tried to give you what I feel are the important areas with regard to it. And so it's all about frequency equals amplitude. Period. And we'll go over this again. And you're going to see, and there's different ways they summate. That's kind of where the starting point is of the new material is. We can cause an action potential not just by how much neurotransmitter, but also how many places it happens. So we can do it spatially or what they call temporally, as you will see shortly. So there's an element of that controls it, and it's a little bit different than the neuromuscular system. So you get the neurotransmitter binding. Typically, they're gated ion channels. Ion channels work faster, as you will see when you get to the neurotransmitters. And it opens those channels. That's the typical sodium goes in, potassium goes out. Big difference here. Typically, when excitatory, the 3 to 2 sodium in, potassium out, just like the neuromuscular junction. Frequently, the inhibitory or less likely to fire are chloride gated channels. You don't see so much of the potassium only channels where potassium goes out. You see a whole lot more of chloride gated channels where chloride goes in and lowers, hyperpolarizes the area along the membrane and makes it less likely to fire. That's the typical inhibitory that we see. And then the usual culprits for reuptake, degradation, diffusion. The big player that we work on is reuptake. Reuptake is the most frequent way that the neurotransmitters are removed from the synapse, other than the ones we're already familiar with acetylcholine, where only the choline is really subject to reuptake. The rest are either degraded or diffused. And so you're going to see a lot of things either are typically in the realm of reuptake inhibitors, stopping reuptake, or ones that tend to have a means of pushing out more neurotransmitter and then also also limiting the reuptake. So there's a lot of nuances. And if you're interested in the pharmacology, all of that is look upable. And at your level, everybody, you just go to the prescribing information. Whatever medication you're looking for, let's say, somebody's on Adderall. Pretty common. It's typically used for ADD, ADHD, some other things that are part of it. And you look at the Adderall and see exactly how it works. So you look at physicians prescribing information, look at mode of action. It'll tell you the receptors. It'll tell you what it's doing at the at the synaptic junction, because it reuptake, et cetera, et cetera. And I covered this a little bit. Delay, to me, that's just the rate determining step from an old chem major, because obviously electrical impulses are going a whole lot faster than that. Okay. So you're when they start talking about 100 or 200 meters per second or 300 miles per hour or whatever, that's not an electrical signal. That's the electrical signal being limited by the chemical signal. Yeah. And you can see that there's lots of different ones, and you can look through these, the concept of memory and abundance in embryonic nervous tissue. And the last thing I did in that one, that I did, was only about a 12 or 15-minute presentation because I ran out of time, was postsynaptic potentials that were there. And again, terms that you need to remember, because I use them on an exam: EPSP and IPSP, not just me, because they're terms that you'll need to know going forward. Excitatory, inhibitory. And understand, there's so many nerves in a circuit. The nerve can start as postsynaptic, but when it triggers the next nerve in a sequence, now it's presynaptic. So, most nerves are doing both. We're going to look at these different nerve circuits a little bit and show you some different ones down the road. So here they are. It's just an accumulation of summation: fire or don't fire. That same old deal. And here's the idea with sodium and potassium in opposite directions, the one that we're familiar with, versus, which is always going to be excitatory because it's always 3 to 2. And again, the whole idea is what makes the polarization, what makes the action potential or the trigger reaching that threshold is if it's sufficient for these changes to be prolonged enough to get to that axonal hillock area where we've got that big concentration of voltage gated sodium, then potassium channels, and boom, we have an action potential. Don't want to rebuild the wheel or do this. Again, chloride is more often moving into the cell. That's what's hyperpolarizing. And they just show you this. And so this is the idea of summation. Okay. They can add together. So whether it's excitatory or inhibitory, and again, most nerves receive a lot of inputs from all these other ones as part of the process of whatever your brain is doing to send signals along the way. And they can summate either temporally or spatially. Temporal is the one you're most familiar with, rapid fire. And so even before this is one over time, one or more presynaptic nerves, so that theoretically it can add to it. It's not going to make, and if you're confused about the all or none idea, this is just getting the nerve that's going, let's say the nerve that something hurts to fire. Okay. There can be a whole lot of things, inputs, finally get the message, right, that hurts. That kind of thing. And then the severity would be how frequently that particular nerve that's telling your brain something hurts fires. Okay. So you could, depending on how many of these little impulses over time, okay, because again, there's a relative refractory period that can be impactful with this versus spatially, how large an area. That's all they're trying to get. So it's not something I would be a test question. I'm trying to understand. You understand there's certain nuances to this. So it can be the number of impulses that are about to trigger that threshold event over space where they're occurring or over time when they're occurring. That's what they're trying to show you. So we can have a certain degree of summation in that, but it's not the same type of phenomenon we look at as staircasing or things like that. It's merely determining whether we get to that threshold or not. And they give you the spatial one. This has a lot to do with therapeutics. When people are taking medications that impact the nervous system, whether we're looking at treating Parkinson's, treating depression, that very, very large category of SSRIs that I mentioned, selective serotonin reuptake inhibitors that are so useful for and utilized, as it were, for depressive activities, eating disorders, obsessive compulsive disorders, etc., etc. It involves what's called synaptic potentiation. By repeatedly using that circuit, okay, we increase the ability of that cell to be excited. Effectively, we're modifying its response to a typical amount of neurotransmitter. Okay, effectively, that's why, and it takes time. That's why when somebody takes one of these things and go, you have what's called a placebo effect. Somebody, I've been feeling a little depressed. Well, here's this thing, I'm having trouble focusing, whatever. And they prescribe some kind of a medication. And they come back in 2 weeks, Doc, I never felt so good. Oh my God, it's all over. We call that a placebo effect. Take a pill, feel better. Typically, these take month to 2 months to really have this effect. And so clinicians, people who do this and prescribe this, are aware of these types of things. It takes a certain amount of time. It's very unusual for the effects to occur right away. So, I mean, there's a lot of psychological science when it comes to patient and physician interactions and anybody's clinicians, or you yourself taking, or somebody in your family taking medicine. So calcium concentration increases, calcium voltage gate is open, etc., enzymes, and this is the idea of learning and memory. When you're using circuits longer, I mean, it facilitates their usage. There's a lot. I mean, there's a lot in the body that's use it or lose it, and this is just another example. Okay, and the same thing, we can have inhibition as well. And they're looking at that, and they're looking at that, and they're looking at that, and I don't care, and I don't care. And finally, oh, thank goodness. It was 14 minutes before I finally got to the important part. The rest of this is neurotransmitters. And there's been a lot of them. We look at about 10. And you see, most nerves make more than one. And therefore, there's a certain inherent versatility depending on the signals that they receive. Okay. And as you can see, stimulation frequencies, we don't go into the specifics of that. The classification first, their chemical structure and their function. The one we've known about the longest, the one we have the most information, the one you already know about, acetylcholine. Best understood, most abundant, every neuromuscular junction. The next chapter we're doing is the autonomic nervous system. It's everywhere in that nervous system except in one particular area where we have epinephrine and norepinephrine. That's it. Okay. Acetic acid and choline, we know about that. We know about the actions of acetylcholinesterase. All of this, just that's the beauty of having done the neuromuscular chapter immediately before this, because you only have to study it once for the same test. That's the way I look at it. All right. First on the list, biogenic amines. So we ingest proteins. When we ingest proteins and we break them down into amino acids, it's funny, the brain can utilize them as amino acids. You will see that shortly. And we can use them as amines themselves. So effectively, what happens typically when we're utilizing them as an energy source, we deaminate first. You're probably aware of this from cell and molecular and from the way things work. With the amino acids come in, we take off the amine group. If we're going to use it again, we can plunk it back on, and we break down from that, and that becomes our many times our building components. In this case, think of removing the acid first, if you want to think of that metabolically. So now you have what's called a biogenic amine. Surely the amino acid with the most relevance in this is tyrosine. Talks about it a little bit when we looked at parts of the brain. For those that recall back from looking at neuroanatomy, you have dopamine, norepinephrine, and epinephrine. The one epinephrine, again, you're going to see is something that's produced at the adrenal medulla. That's we're going to look at that in autonomic nervous system. But dopamine and norepinephrine are the ones that you might recall are being produced typically in the midbrain. It's typically in what's called the substantia nigra. If you recall back and think about that area, so-called black substance, and those pigmented substances inevitably are neurotransmitters. That was the pathway that was involved when we talked about the dopamine pathway that was so important. So you have dopamine and norepinephrine being an integral part of that, and they're both made from tyrosine. Down the road, you're going to see we're not done with tyrosine yet. Tyrosine is a very, very big player when it comes to the endocrine system because that's the framework for thyroid hormone. So that's the first group to remember. The next are called indolamines. So indole is something that can be produced by from different, as you can see here, at least two, without going into the biochemistry. I don't know if you've covered it or not with regard to that. You have tryptophan metabolism, you have serotonin. And serotonin, where dopamine and norepinephrine are typically, with limited exceptions, almost always excitatory, serotonin can go in a variety of directions. Serotonin, depending, has so many subtypes of receptors that has different effects on different circuits or different systems. It's probably the one, as I said, from the selective made by selective serotonin reuptake inhibitors. The selectivity is the receptors, not the serotonin itself. So it's designed to work on specific receptors in specific systems. Those and their effects are sometimes they're excitatory, sometimes they're inhibitory. The whole idea of tryptophan being one that typically is associated with it. If we're looking at a classic serotonin receptors, they are more often inhibitory than excitatory. That's where the concept of foods rich in tryptophan tend to make you tired or sleepy, where foods that are rich in tyrosine tended to be, sometimes people would be accelerate their heartbeat, get headaches, get flushed, that type of thing that were there. And then histidine leading to histamine. Histamine is interesting because it plays a role in a variety of systems in the immune system, which we'll deal with it a lot. We'll deal with it with regard to the blood system, a couple of chapters that are coming up. And certainly, we're thinking about its role with allergies. We're thinking of its role with regard to blood vessel mechanics. But histamine is a potent player in the brain itself as well as a neurotransmitter. And there is so much that's involved with them. And again, the autonomic nervous system, that's the role with norepinephrine and also epinephrine. And really, the crux of treating mental illnesses for the longest time have been with this group. The early treatments for them, when we started to utilize medications, were we use what are called monoamine oxidase inhibitors, called MAO inhibitors. What they would do is they would limit the enzyme that breaks down, and they make dopamine more dopamine and more norepinephrine available. We had things like Elavil to elevate, people, or Melavil to mellow them out. Uh, they weren't terribly effective. There were a number of categories of antidepressants like that. And I think nowadays predominant serotonin probably predominates with regard to all of these amino acids in and of themselves. Okay, that we know are known neurotransmitters. We have things. We have glutamate, aspartate. Typically, they're excitatory glutamic acid and aspartic acid, glycine, and GABA, gamma aminobutyric acid. We always say GABA. Those are both considered typically inhibitory. So we want to go through and look at those. Hold on. Give me 1 second. There we go. Hold on. Just trying to make it because we got stuff going on in the house. Go in here. And so the other thing to look at, as well as those, excitatory and inhibitory, things like that. And we're gonna go over them with additional examples over time. Is these are neuropeptides. So we've got amino acids themselves, biogenic amines, the amino acids themselves, and now we add in the fact short chains called neuropeptides. They're relatively small. Substance P plays a role with pain signals. That's the one that's reduced when you use things like capsaicin creams. Theoretically, it removes substance P from certain areas, not always effective. The endorphins are the endogenous morphine compounds. As you can see, they're natural opiates. There's so many instances. People get a certain amount, and they're pleasure inducing. So it's not that pain equals pleasure. It's just that, people experience, for years they talked about a runner's high, certain types of pleasure they get from exercise. We produce them normally, these gut-brain peptides. They play a role in regulating digestion, but there's also a certain amount of these endorphins are released when we eat. There's a certain amount of pleasure that comes from things like that. There's a lot of things that play that role. So we have and their relationship chemically to opiates, to morphine and morphine analogs, and opium itself. Okay, at least my limited knowledge of it is it's organic chemically similar. That's there. Purines are you're probably all familiar with because we're talking about adenosine. Okay, so here's purine. Okay, adenine and guanine, they're the purines. The one we're looking at is adenosine, good old adenine and ribose. Okay, we even know now that ATP has neurotransmitter effects. It's not clear what they are, but it's definitely been identified. Adenosine basically is an inhibitor. And famously, what does caffeine do? It blocks adenosine receptors, so we can't be inhibited. So what's going to happen? Okay, we're going to basically have signals are going to be more excitatory in nature because there's not the offset of the inhibitory aspect. So what do I do in the morning when you have coffee or a caffeinated drink or an energy drink? Boom. All of those basically work to make more caffeine abundant. And we can overdo the things. Fortunately, excessive caffeine is typically, might accelerate your heart rate or give you a headache. And typically to stop it is addictive in nature for sure. It's one of those addictions that's a little bit easier to deal with for the most part because there's less downside to it. I mean, sure, somebody having significant heart-related problems and that where accelerating heart rate could be a big problem, palpitations, things like that. These are even more interesting. Nitric oxide we'll start to talk about a fair amount. We its role in development isn't clearly understood. Its role in being able for blood vessels to be able to protect themselves by dilating when necessary is very significant. Carbon monoxide, interestingly, has neurotransmitter effects, but certainly it's a toxin. That's hydrogen sulfide gas would classify as that. You can see G protein coupled receptors in the brain. There's other ones that are lipid soluble and synthesized on demand. It's very interesting, those kinds of things. So the nitric oxide, really, the learning, release from brain damage, the role it plays intestinally, the role it plays reproductively. We inhibit nitric oxide. So we inhibit the breakdown of nitric oxide. That's the foundation of erectile dysfunction medications. There's a myriad of things that I can't explain to you. Just to say there's just a lot of those. And the ones that I have information, I'll share. This is the whole idea. We make our own cannabinoids. I mean, when we talk about, legalized marijuana-based products, THC and related compounds, tetrahydrocannabinol is the active ingredient in marijuana, which everybody's aware of. It is a very complex molecule. But interestingly, we make in our own brain variants of it. And when it breaks down, when marijuana is taken in, a lot of its breakdown products, as our bodies metabolize, have interesting effects on their own. It's almost why they're able to do so much now with the legalization, both for medical usage and recreational usage, cannabinol products. Very interesting. Okay. So you can look at some of it. It is lipid soluble, and the idea of being lipid soluble means it is able to get into the brain. Remember, they have the blood-brain barrier, so you can explain why lipid soluble is important, even though it links to G protein receptors. And again, when you have a G protein receptor, it has multiple effects. Inevitably, those G protein systems and second messengers, really very interesting. Again, learning and memory. We've known for a long time, when we first looked at medical usage of marijuana and didn't understand fully about it, people who it was an appetite stimulant, people experienced that early on. It was great for combating nausea. Okay, when you administered pain medications and took that along with it, it had almost a synergistic effect, enhanced pain medicine. It's like for years what we would use commonly when we administer, if somebody was post-op, we give them Demerol, morphine analog. Nowadays they use different ones, and we give them with Vistarol, an antihistamine that relaxes them a little bit. So when you're relaxed, it allows the pain medicine to be more powerful. Same idea here. So by effectively, you could, by utilizing this in concert with a strong pain medicine, you could probably use less of the strong pain medicine. So there's a whole lot of potential usage for it. It's like anything else. When you legalize something that is going to cause you to have maybe alter your attention span, make you somewhat tired, impact your reaction time, just like driving under the influence. It's an influence. Use with caution. Do what you want to do. So there's all the diversity in functions, ones that go up, ones that go down. Let me do this for a second. And now my watch in front of me, that's why I was doing that. So you check our time. And we'll probably get, wrong chapter, sorry. Here. And basically, you can look at this. Excitatory versus inhibitory. Same thing. Depolarize or hyperpolarize. Broad brush. Not always. When we say inhibitory, it doesn't mean you're going to do less. I've said it probably several times. What does alcohol do? Alcohol is a disinhibiting agent. That's why some people, you get somebody who say, well, they're never going to be alive for the party, and have 2 drinks, and all of a sudden they're dancing on top of the table. Okay. You all know folks like this who liquor has an unexpected effect. It's called a disinhibitor. You're inhibiting circuits that normally inhibit certain types of activity. If you inhibit an inhibitor, you basically activate the circuit. Think of it a double negative. That's what happens with some of these. I talked about Adderall. Why do we use a psychostimulant on folks with attention deficit or hyperactivity disorders? Why have they been used for a long time like that? You're stimulating, listen to this, you're stimulating circuits that cause you to inhibit impulsive, hyperactive, things that are atypical behaviors. You're activating your brain center that says, this is not time to do this. Think of it that way. And believe me, I know what I speak. I have dealt with this from a standpoint of, we were at the point, my kids were growing up, every kid that was a little rammy was all of a sudden they wanted to put them on ADD medicine. It's ridiculous. Like it was chronic infectious ADD, idiots. Glutamate, not always, but usually excitatory. Effectively, if you remember, we have some circuits like where glutamate, like within the ear, okay, with hearing and balance, glutamate actually is actually, even though it may cause hearing, in a sense, you might think of it as you're actually inhibiting a circuit. Because remember, it actually does some hyperpolarizations. Sometimes they're odd. And acetylcholine and norepinephrine, you can see there's at least a couple of different receptors that work opposite. Normally they're excitatory, but inhibitory for cardiac muscle. Norepinephrine, usually excitatory, but inhibitory for bronchiolar muscular, because it's going to dilate bronchi. I mean, we'll get into all of these when we look at particularly the autonomic nervous system. This is another important nugget, direct versus indirect. Neurotransmitters that open ion, I said it earlier, if they open an ion channel, they work fast because they alter the membrane potential. Amino acids and acetylcholine, okay, glutamate, aspartate, glycine, GABA, acetylcholine, boom. Indirect, typically the biogenic amines, second messengers, long-lasting, the neuropeptides we talked about, the gases, because when you're going through that G protein passageway, and before you get to sort of that cascading effect of the second messengers, it's certainly taken a longer period of time. Things that take longer last longer. That's an important nugget. For years, it's kind of the idea of a neuromodulator is a lot of things. That there's just other modulation means it's altering the signal in some way, shape, or form. Years ago, they used to think that hallucinogenic drugs or hallucinogenic side effects of drugs like LSD and things that are ecstasy from that category, which are more in the line of hyperstimulants, were really neuromodulators. We don't understand necessarily why all of them work the way they do. So it was a sort of a generic term, at least from the way I was instructed about it. And I taught a course in addictive diseases and in banned substances. And it's all of these things, whether it's synthesis, release, degradation, reuptake, sensitivity, maybe just localized effects. There's so many different ones. We're not going to study specifics, but it's a term that you run into. I think sometimes it's a term when we're not exactly sure how it works. We'll just kind of default and say, "Oh, it's a neuromodulator." Oh, I understand that. Okay. So again, Ion channels, immediate and brief. Sodium influx, inhibitory chloride influx. That's what I told you before. Those are rapid. It doesn't take a lot. G protein link, longer time. We'll get to muscarinics, and that's in the next chapter. Biogenic amines, neuropeptide, all the things that they definitely, and you can see all the things that the second messengers can do. They can open and close ion channels, but it's not immediate. Kinase enzymes, like we'll talk about that when we get to diabetes with tyrosine kinase, phosphorylation, etc., etc. And we've seen this 1,000 times. And I don't do the part with neurointegration. So, I mean, this is, they function together. That's the best thing. And they go into discharge and all the, if you want to look at this, it's fine. I'm not doing the receptors and parallel processing and blah, blah, blah. I think we're done. All right. This is a little early. My voice is kind of, I'm going to, if you want to join at 4:30, if you got something else going on, I've got to give you another one of these. Your day's busy enough as it is. I'm going to start autonomic nervous system. I need to get that done. So I'll try to log on then at 4:30. You're welcome to join me. And let me show you what that's going to be. I will load that for you because I'm kind of talked out today. And here is these, it's just me. This chapter 14, autonomic nervous system. I will get that pumped up on your blackboard in this still. And effectively, that is material that, let me rephrase, that's material that will start our next exam. Our first exam is complete now with the material. That would involve the cell stuff, that involves the neuromuscular junction stuff, and this nerve stuff. So that's done. I will get cracking and have test information on Wednesday, which no way we're going to have it on Monday. It's just too soon for this Monday. So, I mean, for next Monday would be the 24th. It's got to come after that. We'll figure that out on Wednesday. Thank you very much. And I will see everybody joining back at 4:30, or I'll see you live and in person on Wednesday.